So the 2.5 cancel. And then I'm left to figure this out. Got this integral pi over 6 to pi over 2. 36. Can't do anything with that. 9 cosecant squared. I don't really see the need to do anything with that. Okay? Here's why. If I want the antiderivative one way or another, if that's my goal, I know something that, or even if I don't know it, it should seem familiar that, yeah, I know I've heard it before, the derivative of something is cosecant squared somehow, okay? So, and that thing is cotangent. The derivative of cotangent is negative cosecant squared. So let's do plus 9 cotangent theta, okay? All right. Pi over 6, pi over 2. All right, so here we go. The first part's not so hard. I get 18 pi. But what's cotangent pi over 2? Well, we might think of things like that cotangent's 1 over tangent. And so we may feel inclined to say, to do cotangent of pi over 2 or cotangent of 90, we'll do 1 over tangent 90. So I got my calculator in degrees and say I do tangent 90. And then I say, well, I'll just take that answer and do 1 over that. So it'll be cotangent. It says, oh, well, there's no answer to that. Well, so that identity, obviously it doesn't work if there's not an answer to tangent. So let's do like this. We got to think about what cotangent is. Okay, so I'm going to go back, say, to the time when I learned trigonometry. And if I had an angle in standard position and a point on the terminal side, it would outline a triangle. This side is x, this side is y, this side is r. And then I remember that cotangent is x over y. That's the real definition of it. So say cotangent's 1 over tangent. That's an identity. It only applies if tangent is defined, all right? Okay, so anyway, we got to go back to this. This is how cotangent is calculated. So say, now this angle is there for illustration. What if I push this up to 90? Now, what would that triangle look like? If I were to push that up to 90, the x would be 0, and the y and r would be the same, okay? So cotangent of 90 degrees would be 0 over the y, right? I thought I wanted to mention it that way. Okay, we should not, it's easy to forget about these things. I'm not saying that's the only way to figure out cotangent of 90, cotangent pi over 2. But this is the fundamental definition that, you know, even though we don't use it all the time, let's not forget that that's how things are done at the most basic level, okay? So, okay, put pi over 2 here, I get 18 pi. Pi over 2 here, I get 0. And then minus whatever pi over 6 gives me, okay? So this will give me 6 pi. And then cotangent, now here with pi over 6, I really could do 1 over tangent, because tangent of 30 degrees is defined. So tangent of 30 degrees turned out to be 1 over root 3. So cotangent of that is root 3. So I get 9 root 3. Okay, so do with pi over 6 or 30 degrees, say 9 over tangent 30 degrees. So you get like that. So 18 pi minus 6 pi. I'll get 12 pi. And I'll get minus 9 root 3. 12 pi minus 9 root 3. Alright, it's a measurement, it's area. So I go ahead and put square units. Alright, so what was that? That was 10. Agree with my picture, agree with my angles, my setup, in here, that's really just calculus 1 to do all that, but you know, if that's something we got to talk about, we can. And then my answer, my measurement. Anyway, so let's do, so I had one last problem to do, or this last one I had in mind. There might be a few others in the lesson that haven't been addressed in class or in the video, and those will be for you. But it was 14. That was the last one I wanted to do. Calculate the area within one loop of the graph r is equal to sine 5 theta. And to do that, we need to know what a loop looks like, and you know, just like anything, it's a little bit hard to do this problem if you have no clue what you're looking at. All right, so same thing here. So what I thought we would do is discuss the graphing technique, and just I feel better showing you that again. And then once we get the graph, then we'll set it up. Okay. So what was the graphing technique? At least here's what I recommended. You can do it however you want, but I said draw the graph in rectangular coordinates. So that's like theta is on the horizontal axis and r is on the vertical axis. Draw the sine wave, and then convert those points and that pattern over into polar coordinates. Okay. So about this, I noticed it's a sine wave. It has a period of 2 pi over 5. 2 pi is the standard normal period of sine theta. That multiplier of 5 will alter the period, and the period will become 2 pi over 5. So when I drew this graph, I was going to say, well, here's what we do. The sine wave completes its cycle here from 0 to 2 pi, and we'll just divide it into fourths. We'll take half of that is pi over 5, half of that's pi over 10, and then we'll count by pi over 10. 1 pi over 10, 2 pi over 10, 3 pi over 10, 4 pi over 10, 5 pi over 10, 6 pi over 10, if we need to go further, 7 pi over 10. So it's like counting by 18 degrees. 18 degrees, 36 degrees, etc., etc. Okay, all right, now, so that's my layout. Now, the reason I choose those points, or the reason of all angles you could have to draw the graph, the reason I choose these is because you'll get ones and zeros if you do it that way, and that's nice. Okay, so the sine wave starts at 0, goes to its maximum value of 1, back down to 0, then to its minimum value of -1, then back up to 0. And then that pattern would repeat. And if you want to draw more, just be like that. Okay, how much you need to draw, I guess that's up to you. I drew a little bit more than I had to. Just really to show you that you can. Okay, so here's the best it's going to look today. Me drawing it freehand. Alright, so that's at least what this looks like from 0 to 3 pi over 5. Alright. So anyway, now let's convert the pattern and the points to get an idea of what the loops even look like, or what the angles might be to set this thing up. You know, I've got to figure that out. So here goes. So let's say this is in polar coordinates. I convert these points and that pattern to polar coordinates. Very first point is that theta is 0 and r is 0. So that would be right here. You know, this, alright, that's theta is equal to 0. Okay, this theta is equal to 90, right? That's how we do it. So if theta was 0 and r was 0, that's what you get. If theta was 18 degrees, r would be 1. So I'm going to do like this. I'll actually put a mark 18, and like that line right there, that's theta is 18 degrees. And okay, let's say that I gotta have a scale. So 1 inch means 1. Okay, so there's your point right there. Is that point up on that other graph. 1 for r, pi over 10. Pi over 10 being the same thing as 18 degrees. Now, what it says is that as r increases from 0 to 18 degrees, or as theta increases from 0 to 18 degrees, r very gradually goes from 0 to 1. So we would get an arc, like, you have to be something like this to do that. Okay? But then again, as I go from 18 to 36 degrees, let's put 36 degrees on there. So here it is, this faint line right there. That's theta is equal to 36 degrees, or pi over 5. As theta goes from here to there, r diminishes back from 1 to 0, all right? So there's one of many loops on this graph right there. Okay? Now, if you like to see the way I did it in class, I'd say, see this section 1 from 0 to pi over 10? That gives you this arc right here. And see this section from pi over 10 to pi over 2? Then that gives you this arc right there. Okay. So I don't know. So that's what it is. I could draw more of it, but it takes so long to do it. I mean, what I'm hoping, what you have to tell me otherwise is that you say, yeah, we could finish it if we had to, right? We get it. Convert one section at a time. Put the angles for reference. You'll get lots of loops. Okay, you have to take this pretty far to get all of them. But let's say that we just needed to see what one loop was and the area within one of them. Now I think I have what I need. You want to go from 0 to pi over 10, and then you want to double it, because this wedge right here, that would get me half of the area that I want. So make sure you see that. I'm saying that I'll set it up with this. Okay? That wedge will get me half of the area of a loop. Alright, so we want to go from 0 to pi over 10, 1/2 r squared d theta. What's r? What's that arc? What's that polar graph? It is sine 5 theta. Alright, so that shouldn't be too hard to do. So for this part, I'll say, see the picture. The area totally contained within a loop is going to be double the result of the integral from 0 to pi over 10. Okay, 1/2 r squared, which would be like that, d theta. Okay, I like to use symmetry. The 2 and the 1/2 are gone. Now I get like so. And we have this identity that sine squared of an angle is 1 minus cosine of the angle twice as big, all divided by 2. So what we're going to have to say about sine squared 5 theta is this 1 minus cosine, what's the angle that's twice as big as that one? I don't know what else to say besides 10 theta over 2. Okay, agreed? That's the identity. And this is two separate terms. 1/2 gives me theta over 2. And cosine 10 theta over 2, separate term, gives me sine 10 theta over 20 as the antiderivative. Alright, well this one's not, now that we got to this point, not going to be very hard. Pi over 10 gives me pi over 20. Pi over 10 there times 10 gives me pi. Sine of pi is 0. And then 0 here, and here gives me 0. It's just pi over 20. Pi over 20 square units. Not very big. Like 3 over 20. Okay. Alright. So it's up to you then. You watch my video. You can see how we can do this and get this, and we can take it further. You can go to Wolfram and you can draw this entire thing. Just type in polar plot. R is equal to sine 5 times theta. And if you want to, just for practice, you could try to graph this whole thing, every single loop yourself, and then check it with Wolfram. There's at least one of them. I think it might have 5 to 7 loops total. All right, but it would take a while. It would take a while to do that. But if you can do these, in theory at least, you could do the rest of it, because the understanding is the same.